Okay, so I guess we can begin. It's a great pleasure to introduce David Wahiche from the University de Tours. I don't know how to pronounce it, uh, uh, but he'll talk about from McDonald identities to Nekrasov-Okunko formulas, type formulas. Over to you, David. Can't hear you for some reason.
Yeah, I forgot to unmute myself. Sorry. So thank you, Gaurav, for the invitation. So what I'll talk today about are some results that are extracted from my PhD and can be found on archive, where the title is rather long and probably unreadable, but it's from Magdalene identities to Nekrasov-Okunov type formulas. And I'll also try to so I was doing my PhD under supervision of Frédéric Jouet in Lyon, and then now I'm a postdoc within the ANR Cortipom at the University of Tours under the supervision of Cédric Lecouvet, and I'll try to mention some partial results we had with Cédric with respect to what I did during my PhD. Okay. So what I'll try to do is to connect the so-called Magdalene identities on the one hand. So let me recall the definition of the Dedekind data function. So T is here a formal variable, and it can be seen as a formal power series in of a weight 1/2. And this is unconventional, but ever since I'm going to talk about Q analogs, I wanted to avoid this confusion. So it's not the Q Pochhammer symbol, but the T Pochhammer symbol. And so Magdalene in 1972 came across this identity trying to find the combinatorial expansion, the power series expansion with respect to the formal variable T of this Dedekind product. So he wrote a paper on the connection with some powers of eta, and exploring the connection with affine root systems, infinite affine root systems for Lie algebras. So it's an identity of the type sum equal to product, where on the left-hand side you have the sum part with the sum over some sublattices of ZT, where you have some constraints on the vectors of integers, and on the right-hand side you have a product part. On the other hand, ever since I'm trying to go from the from Magdalene identities to Nekrasov-Okunov formula, I'm introducing the Nekrasov-Okunov, so-called Nekrasov-Okunov formula, which was discovered simultaneously by Nekrasov and Okunkov on the one hand, using gauge theory, and Westbury on the other hand, more coming from representation theory. And later it was rediscovered by Hahn in 2008, using combinatorial methods. So it reads as follows. I'm going to define all of the subset I'm mentioning, but P here stands for the set of integer partition. This corresponds to the weight of lambda. H of lambda is a multiset of hook lenses, and you have a product over all of the hook lenses. And on the right-hand side, you have the product part. And the approach of Hahn to prove and to derive this identity for any complex number Z is basically to give a combinatorial interpretation within the world of integer partition of the Magdalene identity here, and then use a polynomiality argument to lift this identity to any complex number Z. Okay. So first of all, what are the Magdalene identities? So if you're familiar with the finite root systems and root system in general, which I'm not gonna, I won't exactly discuss here, but if you take a finite root system R and the wild group associated, basically the Weil denominator formula reads as follows. So it's a sum equal to a product over the positive roots. So I gave here the example of A1, with R being the root system and R plus being the positive roots. So one way of looking at Magdalene identities is to see it as a generalization to a fine root system of the Weil denominator formula. And sometimes it's also called the Weil-Macdonald-Kax formula, denominator formula. And you have the sum here. So W is replaced with the affine wall group. And the root system is replaced with an affine root system here. And I gave here the example of A tilde 1. So in this case, one can see that, so this is called the imaginary root, but I'm not going to exactly discuss it within this talk, but basically one can think of, it's basically you take the classical root of A1 and you just add n times delta, delta being, you can think of it as a 1, and where n is any integer. And now if you're looking at the positive roots, you have the positive root affine roots, you have the classical positive roots, and then some other values. The thing is, and the important remark, and sorry, I forgot the parenthesis here, is that basically if you remove R plus, those stats, they are symmetric with respect to n. And this is going to be important ever since one way of going from Magdalene identities to Nekrasov-Okounkov formula is to, the first step is to rewrite the Magdalene identity as an identity over some symmetric functions. And we are to derive then by the product of all classical positive roots, each side of this identity, and then rephrase it and reformulate it within the basis of characters associated to each type. And then by some enumerative results, one can derive Nekrasov-Okounkov type formulas. So it was, it can be, given that formulation of Magdalene, it was rather, at least for me, blurry at the very beginning. So one reformulation of this identity is as follows. It can be found in Carter's book, and they're decomposing the Magdalene identities as a sum of characters with respect to the while group, so not the affine one, so it's a finite root system here, as a decomposition over virtual characters. Here, G is a parameter that comes from the root lattice. And actually, it's in all of the cases we are to consider the dual Coxeter number, apart from type C, where it's twice the dual Coxeter number. Okay. And more specifically, the reformulation and my starting point for most cases during my PhD was a reformulation by Stanton or Rosengren and Schlosser for the 7 infinite affine types. Where they reformulated this identity within the world of multivariate power series, sorry. And basically, so this GM becomes sublattices of ZT following a geometric condition, and where you set xi to be exponential minus epsilon I, where epsilon I is the is vector of the canonical basis of Cn, for instance, or Ct in this case. And think of it as exponential minus 1 here. Okay. In the attempt to understand better the connection between what I did within the world of multivariate power series, where I decompose the Magdalene identities in the basis of Schur functions, symplectic Schur functions, special orthogonal Schur functions, the fourth reformulation we found with Cédric Lecouvet is that the Magdalene identity, if you divide both sides of this identities by the classical root system, becomes a symmetric, this product becomes a symmetric function in the xi's, and then it can be reformulated within the basis of character. And actually, it gives this nice decomposition where you're trying, instead of summing over virtual characters, you're now summing over the character indexed by dominant weight. So think of it basically as a partition. With epsilon C being the signature of the affine Grassmannian. And this basically is going to be interpreted as either the weight of some integer partition or half the weight of some integer partition. Okay. So for instance, in type A, so the Weyl group is basically a permutation, and the affine Weyl group is an affine permutation. So what is an affine permutation? It's basically a map which is bijective between Z and Z. where you have this shift condition, and you have also this summing condition, where the sum depends on t. So given the property of shift, one can think of those affine permutation as purely characterized by what is called the window, which are the t first element, first value, positive, strictly positive value of sigma tilde. Okay. Also, this condition, it gives the fact that sigma tilde j, sigma tilde I are all have all different congruence mod t, and this is an important thing. And so the affine Grassmannian, in this case, can be thought of as this window being particularly ordered. So in strictly increasing order, they cannot be equal ever since their residue mod t. Each of those residue are different mod t. Okay. So the Weyl formula in classical type A(t-1), so the finite root system, can be rephrased as follows. It's basically the Vandermonde determinant. Okay, where on the left-hand side, the sum is replaced with the determinant. Actually, given the fact that the Weyl group is a group of permutation, it's basically a reinterpretation of the sum, a combinatorial interpretation of the determinant, which is the sum over over the permutation of the element of the matrices. Okay. So the reformulation which was my starting point, as I said, was a reformulation of the Magnol identity by Stanton and Rosengren and Schlosser, where it is seen as a multivariate generating series. So on the left-hand side, you have a sum over all lattices of ZT with this geometric condition. So the sum of all components are equal to 0. The dependence in MI is highlighted in blue. And here you have some quadratic form in MI. And this quadratic form is going to play a central role in this talk, because this is this interpretation of this quadratic form as some weight or half the weight of integer partition that's going to give us and build the dictionary between the Magnol identity, the hidden subset, family subset of partition that naturally appears when you're looking at these quadratic forms, and then the normative results that are actually required to derive Nekrasov-Okounkov type formulas. On the left-hand side, you just have here the product of imaginary roots, and here the product of classical roots plus, so it was the case where n was being positive, and here the case where n was being negative. And as you can see here, this product is not symmetric yet. Okay. So the goal here is basically to rephrase those formula and to give that a particular meaning within the world of integer partitions. So given the fact that we want to rewrite those formulas as indexed by some characters with dominant weight, indexed by partition, we want to build a dictionary between this multivariate power series and partitions. So what is a partition? A partition is basically non-increasing sequence of strictly positive integers, and it can be naturally represented by its Ferriss diagram. So basically, in this example, you have the partition is 4, 3, 3, 2. So the first row is lambda 1, it's 4 boxes, 3 boxes, 3 boxes, and 2 boxes. And another statistic that is going to be of importance in this talk is the Durfee square. What is the Durfee square? It's basically the largest square that can fit within the Ferriss diagram of the partition. So here it's 3. The weight of the partition is basically just the sum of all the parts. So it's 4 plus 3 plus 3 plus 2. So it's 12 in this case. Okay. Okay, so now if you want to add some more constraint to partition, let me introduce the set of distinct partition. So it's basically it can be seen as a Ferris diagram with no consecutive part being equal. So in this case, for instance, 5, you could not have the partition with a second part equal to 5. So I take the distinct partition, and then I'm going to shift the first row by 1, second row by 2, and the third row by 3. I'm going to then double it and flip it. So I have 2 distinct partition shifted, and I'm going to glue it. So glue those 2 parts together, and it gives a subset of partition, which is the double distinct partition. And it was widely studied by Garvan, Kim, and Stanton, by also Koike and Terada. And one way of looking at those partition, instead of this double distinct construction, is just to see it as, if you remove that yellow strip here, this axis, which is the main, which I will call the main diagonal of the Ferris diagram, is an axis of reflection of this Ferris diagram. In this case, we say that the partition is self-conjugate. So basically, if you remove this, this axis delta is an axis of folding. And those subset of partition are going to be of importance when the while group is no longer a permutation set, but where you have some sign statistic and some properties of folding that naturally appears when you look at other types on type A. Okay, so I mentioned the hooks of partition. So what is a hook? It's basically a collection of boxes. So in this case, the hook associated with this box consists in the collection of boxes that are strictly below, strictly to the right, plus the box itself. So one can see and look at a hook as basically you're entering that way through the Ferris diagram and exiting that way through the Ferris diagram. One can associate the hook with its hook length. So here it is what is called the leg. So it's the number of boxes that are strictly below to this box. To the right, the arm, the number of boxes that are strictly to the right in the Ferris diagram, plus the box itself. So it's 3 boxes plus 2 boxes plus 1. And you have, hence the hook length associated with this box is 6. Okay, so one can look as, one can fill the Ferris diagram of a partition with the multiset of hook lengths. So basically, I just filled here all of the boxes of the partition with the hook lengths with repetition. So this is why it's a multiset. Another subset of another multiset subset of H of lambda that is going to be of importance is HT of lambda. So what is HT of lambda? It's the multiset of hook lengths that are congruent to 0 mod T. Okay, so I shaded here in red all of the boxes whose hook length is congruent to 0 mod 3. Okay, I illustrated the properties of symmetry along double distinct partition along the main diagonal here by coloring H3 of this partition. As you can see, the hooks here are the same. It goes with the fact that this is a folding axis of the Ferris diagram. And if you remove it, all of the hook lengths from that side of the main diagonal are the same as those ones. Okay. So in type A, the geometric condition, which is the sum over some vector of integers components being equal to 0, is actually in bijective correspondence with the set of T-core partitions. What are T-core partitions? T-core partition consists on all partitions that have no hook equal to T. And it is not trivial, but it can be seen computing the literal decomposition, which I'll introduce later, that it is equivalent of having no hooks congruent to 0 mod T. So whenever you have a hook that is congruent to 0 mod T, it implies that you actually have a hook of length T. Okay. Another statistic that is going to be of importance, given the fact that we're considering the subset of partition with properties of symmetry along the main diagonal here, delta, is a sign statistic. So you can think of it as the sign of the content. And basically, if you're above delta, the delta included, you will fill it with the sign plus, and otherwise with the sign minus. Ever since you doubled the partition, and I mentioned that for some types, you're going to have half the weight of a partition. It's basically this part is sufficient to determine the other part. So it's kind of the necessary information, and you can think of it also as a balance. So this sign was introduced and studied both by King and Pétréol, combinatorially, to derive a Nekrasov-Okounkov formula in type C. Okay. So now I have introduced the Magnol identities on the one hand, the integer partition on the other hand, and now we can state the Nekrasov-Okounkov formula properly. So here P is the set of partition, H of lambda is the multiset of hook lengths, and you have this product here, which is like the T-Pochhammer symbol. An important remark made by Hahn was basically that if you take Z equal to T, an integer, then this product, it becomes 1 minus T divided by H to the square. And whenever lambda has an element, a box whose hook length is equal to T, this product actually cancels. So you kind of have this natural filtration on T cores when Z is a strictly positive integer. So the proof of by Hahn was basically this. So you state this case in as the sum over general partition, but you take Z being equal to an integer, and you're going to use the Magnol identity to show that actually this identity, so the sum over all T-core partition here, corresponds to actually the left-hand side of the Magnol identity I showed at the very beginning of the talk. Okay. Later, so in 2018, and it's funny how Nekrasov-Okounkov formulas seem to have like similar timing of publishing when it comes to extension. Reins and Warner, on the one hand, and Carlson and Rodriguez-Villegas provided a QT analog. So here, so it's a bit, so T here is no longer an integer, but it's a formal variable. And L of S is the leg length of the hook length, and A of S corresponds to the number of boxes in the arm of the hook. Okay. So why do they call it first of all, yeah, why did they come across this kind of formula? It was motivated by the study of mixed Hodge polynomials by a paper by Tamas Hausel and Rodriguez-Villegas. And they wanted to solve some conjecture about some character varieties. And this is the case of genus 1. So I'm not going to get into details within this talk, but yeah. And so the approach, what is fun is the approach. The approaches are quite different. Reins and Warner, on the one hand, they focus on the connection between Magnol polynomials and mixed Hodge polynomials on the other hand, and they derive new skew Cauchy-like identities for Magnol polynomials, and they're able to find back this kind of formula. On the other hand, Carlson and Rodriguez-Villegas, they use a proof using vertex operators and the platistic exponential. And so vertex operators are related and correlated to what I'm going to present in this talk. When you look at partition, no longer as a kind of collection of boxes, but with their Maya diagram. So I'm going to get my hands around it afterwards. So why is it called the QT Nekrasov-Okounkov formula? So if you take the special case of Q being equal to T, you have now Q is Q to the power of A of S plus L of S plus 1, which is exactly the very definition of the hook length. So now it becomes a product over all of hook lengths of lambda on the left-hand side. But still, it is not a Nekrasov-Okounkov formula per se, because we don't have the classical Nekrasov-Okounkov formula. It's not, I think it's not that evident and obvious how one can derive the Nekrasov-Okounkov formula that I've showed at the very beginning like this. And the remark made by Reins and Warner and Carlson and Rodriguez-Villegas is that this identity corresponds to a special case of a theorem proved by De and Han, and also simultaneously. So this was done commentarily using a complicated object that does not, who do not extend well to other types by De and Han, and by Iqbal and Al and co-authors on using vertex operator and some refined topological vertex operators. Okay, so in this formula, if you set U equal B to Q to the power of Z, Z being any complex number, and you let Q go to 1 by L'Hospital rule, what you have here is the product of H plus Z times H minus Z divided by H to the square. And this is exactly the Nekrasov-Okounkov formula. The left-hand side, the right-hand side, sorry, can also be rephrased as a T-Porshammer symbol in this case, but it's not that obvious in my opinion. Okay, so now that I have introduced most of the things that I need in this talk, how one can go from Magdalene identities to Nekrasov-Okounkov type formulas. So as I said in the beginning, Magdalene identities, they are identities parameterized by sublattices of ZT and an affine root system. This sublattices can be rephrased as some being in bijective correspondence between with some subset of partition, thanks to the Littlewood decomposition, which I'm going to introduce a bit later. Okay, so basically you start from Magdalene entity on sublattices on ZT. You're going to use the Littlewood decomposition to rephrase those sublattices as a sum over some subset of partition. When you do this, what naturally appears is that you rephrase it within the language of integer partition. So now you're going to have this action of the Weil group that is going to be a determinant. And the determinant is, and the division plus the division by the roots of the classical root system here is what is going to give you the decomposition in a sure basis. Once you have this, use an enumeration theorem to transform the sure character into a product over all of hook lengths, and then you can derive a Q Nekrasov-Okounkov formulas by specializing the xi's that we took at the very beginning using the reformulation by Olsen and Schlosser, and a polynomiality argument. So what is a sure function? A sure function is basically indexed by a partition, and it's a quotient of determinant. One way of looking at this is basically in this product is if you actually do the transposition, xi become xj and xj become xi, you're going to have a sign, the sign of the transposition, given the fact that the determinant is bideterminant, and you have the same phenomenon that appears to the denominator. Hence, it is invariant by this transformation. So one way of looking at this is to see that sure functions are naturally functions that are invariant by the action of a permutation. It can be thought in many ways. So you can think of it as the orthonormal basis of a symmetric polynomials for a well-chosen scalar product. It is not obvious that those functions, they are actually polynomials. And one way of looking at this is to see them as the sum over Young tableau, and then it is obvious that this is actually a polynomial. And in our cases here, we're going to think of it as a type A character. So basically, as something that is invariant by the action of the Weil group. When you think of it that way, it naturally extends to other kind of Weil groups. So in the example of type C, the while group can be thought of. So what I'm here, those are the finite while group, so not the affine one. You can think of them as an affine, as a sign permutation. So basically, you have it can be thought as the quotient of two determinants, where you have the same invariance by transposition. If you transpose the xi's and hj, it's invariant because of the bi-alternate property of the determinant. But you also had one more invariant, which is the invariance between for the change of variable xi becomes 1 divided by xi. And also you use fully the fact that here this is a quotient of determinant, and then it is invariant also. So the sign of the permutation here can be thought of as replacing xi by 1 divided by xi. Okay. So I started to mention that the main tool to build the dictionary between the Magnol identities and some subset of partition was the little decomposition. And it is the key ingredient to map bijectively lattices that naturally arise when looking at the infinite fine root systems and the subset of partition. And also, it gives you the connection between the weight or half the weight and the quadratic form. And the quadratic form is the quadratic form that was to the exponent of the formal variable t in the exponent in the reformulation by Rosenhill and Schlosser that I showed at the beginning. Okay. Please don't hesitate if you have any questions, by the way. So Littlewood decomposition is a bijective map between partition on the one hand and a couple of a T-core partition and a tuple of integer partition on the other hand. So this is called the T-core. It means that I recall that the T-core is a partition with no hook equal to T. And this is the T quotient, which is can be thought as T-independent partition. Okay. In the case of double distinct partition, given the properties of symmetry along the main diagonal delta, so remember that the main diagonal delta is basically the folding axis for self-conjugate partition and the folding axis of double distinct partition when you remove the yellow strip. And given this property of symmetry, you have a discussion that naturally appears on the integer you're performing the little decomposition. Here you can see that it depends on t being a strictly positive integer. So when t is odd, the little decomposition behaves nicely in the sense that now it's no longer just a couple of a pair of a T-core partition and a tuple of integer partition, but it becomes a triple of double distinct T-core partition, double distinct partition, and T minus 1 divided by 2 partition. And so T here is replaced with T minus 1 divided by 2, and this is exactly because of the property of symmetry along the main diagonal. When T is even, the little decomposition is slightly more complicated in the sense that you have still a double distinct T-core partition, a double distinct partition, T divided by 2 minus 1 partition, and then kind of a fixed term appears, which is the self-conjugate one. And what I mentioned when I introduced the T-core partition was basically that having a hook being equal to T, a hook length being equal to T, is equivalent to having having no hook equal to T is equivalent to having no hook lengths congruent to 0 mod T. And to see this, one useful description is to see lambda partition as in bijective correspondence with P of lambda, which is a bi-infinite binary words of 0 and 1s. So the classical, this has many names. It can be thought of as the Maya diagram, for instance, the Dirac decomposition. It has connection with the beta set as well. So how one can explain this binary correspondence? So basically, what we're going to do is we start along to minus infinity on the y-axis, and we're coming, and every time we do a vertical step, we read the letter 0. So we read first an infinite number of zeros, then we read an alternating 1 and zeros until we arrive on the x-axis, where you go to the infinity, and then you read an infinite number of ones. So what you're going to do is walk around the border of the Ferris diagram. And one important remark is what happens if omega here is the empty partition. If it's the empty partition, you read an infinite number of zeros, and you arrive to the origin here, and then an infinite number of ones. So hence, the empty partition is parameterized by an infinite number of zeros and an infinite number of ones. Okay, but what I want to do is to have this correspondence being indexed by Z. So in order for me to have a correspondence which is unique, so bijective, I need to set the origin of time. So it's just a matter of convention. I could have taken the convention that the origin of time was just before the first one, or just after the last 0. But while for the purpose of this talk, my convention here is to take the origin of time as just after the corner of the Durfee square. Okay, what does it imply? It implies that you perform as many horizontal steps before this point as vertical steps after this point. So it basically corresponds that you have as many ones with negative index and as the same number of zeros of positive index. Here, the letter 1 is the letter indexed by 0, so it's C0. And in this case, omega is a specific partition. It is double distinct partition. This is why I shaded in yellow here, this vertical strip. Okay. So one way of looking at double distinct partition is basically to see them that the first letter of index 0 is forced to be a 1 because of that vertical strip. The other thing is, given the properties of symmetry, the 1 here becomes a 0 there. The 0 there becomes a 1, and etc. Because you have this property of folding. And what we're working on with Frédéric Lecouvet at the moment is to actually formalize this within the language of affine permutation. So kind of there is a natural action of the affine permutation group on those objects and those indices. Okay. So now I claim that the example that I'm presenting now is a double distinct 6-core partition. So what I do is I color the first arrow in red, then second one in actually I color all of the arrows in 6 different colors so that this arrow and this arrow are separated by exactly 6 letters. Okay. Why do I do that? It's because I'm going to extract the subwords. But first of all, let me remind you that when I'm introduced the hooks, I said that one way of looking at hooks was basically to see as you were array entering through the Ferris diagram through 1 and exiting through this part, so parallel to the x-axis through a 0. Hence, all of the boxes of the partition, can be mapped bijectively with the indices of the letter 1 and the letter 0. And the hook length corresponds to the difference between this index with this index. And what I claim here is that there are you cannot find 1 preceding a 0 with exactly a multiple of 6 letters in this diagram. And this is equivalent to the fact that you don't have a hook length that is congruent to 0 mod 6. Okay. So the corresponding word, and with the P of omega, in the case of T being equal to 6 here, is this one, where I kept the color of the arrows. Okay, so how one can perform the little root decomposition from this word. So basically it consists in extracting all of the subwords with fixed congruence index of letters mod 6. So this word in gray consists in all of the letters whose index is congruent to 0 mod 6. This one in red consists in all of the letters congruent to 1 mod 6, and etc. Okay, doing that transform, yeah, I forgot to mention that the origin of time is really important. So this letter, remember, I recall that this letter is actually the first letter, so it's indexed by 0. And if I want to perform this construction, it is essential to be able to trace back this hash bar. So the inherited hash bar within the subwords is what I kept track here. So with this information of this bar, I can reconstruct the original world and go from this construction to this construction. So what we did here is basically construct the quotient. But if you remember the example that I mentioned about the empty partition, it's an infinite sequence of zeros and then an infinite sequence of ones. So basically, it's just those partitions are all empty. But they're all empty, but they don't have this balancing condition of zeros having negative index and of zeros having positive index and ones having negative index with the same cardinality. So this bar is kind of shifted. And that's exactly the Garvan, Kim, and Stanton decomposition for T cores. So what is it? It's basically you have T cores on the one hand and a vector of T integers on the other hand, where they sum to 0. The sum of the components sum to 0. So it's exactly the lattices that I mentioned in type AT tilde A T minus 1 at the very beginning of my talk. So it is this approach of Garvan, Kim, and Stanton paper that gives you that helps you build the dictionary between like the infinite affine root system and some subset of T-core partitions or almost T-core partitions. And what is the shift? So I said that I wanted to be able to build to starting from empty partition. So I want to be able to go from the subwords to the word psi of omega here. And what I need to do is to be able to place this separating bar here. What I'll do is encode it with the charge. What is the charge? So this word is properly written here in the sense that you have as many zeros of positive index as ones of negative index. So the charge here is 0. And it's going to always to be the case for double distinct partition. The charge here is this bar is shifted to the left. So the charge is 1. This one is shifted by 2 to the right. So it's minus 2. This one is always 0 also, because remember that in the little decomposition, the part of the quotient when T is even, and that is the case, is a self-conjugate partition. So the folding condition also guarantees that this one is always going to be properly written. And then you fill it with the vector of charges. Okay, so now if you have the charges, you're able to reconstruct the original T core partition. But the remark is that in the case of double distinct partition, actually, if you have, so this component is always going to be 0, so you don't need it. The minimal, also this one is always going to be 0, so you don't need it. So the minimal information required to trace back and reconstruct a double distinct 6-core partition are the first 2 components of this vector. Okay, because this one is opposite to that one, and that's exactly the folding condition along this corner of the first diagram that gives you that, and this one is opposite to that one. Okay. So what I'll introduce here is the notion of V2T plus 2 T coding. So in this example here, T is equal to 2 and 2T plus 2 is equal to 6. Okay, so as I said, one can look at the Garvan, Kim, and Stanton bijection when you restrict it to the double distinct 2T plus 2 core partition as in bijective correspondence with the vector of ZT with no condition. And what is V2T plus 2T coding in this case? So 2T plus 2 is equal to 6 here. It consists in an ordering of the letter ones in psi of omega. And remember when I mentioned the affine Grassmannian, I said that in type A, it consists in some sort of ordering condition. So our claim with Cedric and what we're working on it, it's actually that the V2T plus T coding, for instance, they correspond to the affine Grassmannian element for type C. Okay, so you take the maximal element of this vector, which is 2, you multiply it by 6 in this example, so it gets 2 times 6, 12, plus 4, sorry, and you have 16. And 16, it corresponds in the indices in psi of omega of the first letter 1 congruent to 4 mod 6, because this corresponds to the elements that are congruent to 4 mod 6. Okay, so naturally, reading the word from the right to the left, we have this ordering condition where the second one, V2, consists in the second biggest element, and it corresponds in the indices of index of the first letter 1 congruent to 1 mod 6. It corresponds to this one. So in the end, what you have is you keep on with that thing, and you have an ordering of the indices that way. And this is what we think as the connection between this vectors of integers and the elements of the Grassmannian. And as you can see, given the properties of symmetry, those ones are always going to be fixed in this case. They correspond, remember, to the letter congruent to 0 mod 6, and those ones congruent to 3 mod 6. And those ones, they are explicitly given the fact that I'm using this vector to define this V coding by those elements. So you just need those 2 elements from the V2T plus 2T coding. Okay, so these notions, they actually extend to the 7 other affine types. Okay. So now I said that we need this tool to rephrase the Magnol identities as a sum over some integer partition. But now, as we're going to see, the Magnol identities are indexed with some characters. And what we need is to transform those characters into Hook-Lens product. And this is exactly what this enumerative theorem gives you. And it works so the fact that it is purely enumerative and purely telescopic product is the fact that tau is any function. Epsilon here, recall that it is, I mentioned some balancing sign statistic at the very beginning, whereas where it depended whether you were above the main diagonal of the Ferris diagram or strictly below. This is this sign. So you have the product over all of the Hook-Lenses of 2T plus 2 core partition on the left-hand side. And on the right-hand side, you have this product where alpha of I of omega depends of omega. And you have this product. So this is strongly connected and related to the affine Grassmannian, and we're still working on it with Cedric. But if you're familiar with it, this product, it corresponds to the determinants of type B. What is a bit painful in this case is that we have this family naturally appearing for an identity of type C, but still. Okay, so the reformulation with respect to the affine Grassmannian that I mentioned at the very beginning, or the manipulation of multivariate power series that I did in my PhD, it reads as follows. You can rewrite by symmetrizing the right-hand side of the Magnol identity. So symmetrizing is just basically dividing both sides by the positive roots of the finite root system. And so you have a sum over all 2T plus 2 core partition, a sign statistic, which is going to be the signature of the affine Grassmannian. The formal variable here now consists in half the weight of a partition and a character of type C, which is a symplectic true function indexed by mu. And mu here is defined explicitly with respect to the Vt plus 2t plus 2t coding of omega, but it's not omega. So this is exactly where this theorem will come in handy. It enables you to transform a product, property that depends on the partition mu as a product of occurrences on omega. Okay, so what I showed and tried to sum up of what we are getting with this approach is a reformulation of magnitude identities for all types. So the family naturally arising here is the family of T cores. Here, it's not exactly 2T minus 1 cores, for instance, but it's almost 2T minus 1 cores, but they have an element of the T quotient of the 2T minus 1 quotient, which is not trivial. What the character nightly appearing are the character of all orthogonal, and the signature of the affine Grassmannian is given by this sign statistic, where G here is 2T minus 1. G of lambda, I forgot to mention, it's the length of the side of the Durfee square. So why do we need those kind of things? We need those kind of things because when you are specializing the Magdal identities for each type, you're going to transform the characters into products of hook lenses of this subset of this family of partition. And you want to use a polynomial argument. So you need those statistics that do depend on T to be removed. And that's the beauty of this theorem, is that they disappear because of this part in the theorems. Okay. Why do you need them not to be dependent on T? It's because you want to use this polynomiality argument. And remember, at the very beginning, when I mentioned the Nekrasov-Volkonkov formula, you want to be able to go from a sum that depends on, that is over T co-partition as a sum over all partitions. So you want to use that polynomiality argument, and you want to have objects that have meaning, even if you, no matter what T is. So here, the side of the Durfee square, for instance, does not depend on T. It solely depends on the partition. And so this is the example of the pure Nekrasov-Volkonkov formula in type C. And given the fact that when you have this enumerative results on hook lenses for type C, what naturally appears is determinant of type B, and what is hidden behind symplectic functions are determinants of type C. One need to compensate. Fortunately, we're able to do it, but delta plays here a special role. So delta, remember, is the main diagonal of the first diagram. Okay. So in the end, you're able to derive actually for each type 7Q analogs. Actually, you're able to derive more than 7Q analogs because of the type tilde BC. And from all of those types, we're able to specialize them and to get 14 Nekrasov-Volkonkov formula. And those 14 Nekrasov-Volkonkov formula, they correspond to the 14 specialization of Magdal identities in the appendix of his paper on a fine root system connecting with Dedekind eta function. Okay, so what are the perspectives? So first of all, what we're working on currently with Selik is to explicit the connection with the affine Grassmannians between those objects and the affine Grassmannians for each type. Also, trying to find an interpretation of the hook length formula that are here as some thing on affine Grassmannian, and also the connection to hook content formula. What I didn't mention is that the theorem of type C that I showed here do exist in type A. Obviously, it was discovered by Han and De, and I also have a proof with those objects in my in the preprint or in my PhD. And it actually connects to a hook content formula with any tau function as well. So one need to find the connection. Then what is hidden behind the idea of Maya diagrams or beta set, for instance, is the idea of vertex operators. So what I'm currently working with is the exact connection of the tools that I used to do the little decomposition and the vertex operators objects. Finally, if one wanted to derive Qt analogs, it'd be interesting to see what are the lengths of those formulas with McDonald polynomials, for instance. And the goal would be for us, to be able to derive Qt analogs. And thank you for your attention.
Thank you, David. Very nice talk. So any questions or comments in the audience?
Yes, I have a question. Well, thank you very much for your nice talk, first of all. And then in some cases you have Qt, or there are Qt extensions. What about also splitting up U in two parts, U1 and U2? Could that also be possible?
Yeah.
Let's say here.
In that
for
case?
Instance, yes.
Yeah, actually, so this question, so they did not do it in their paper in Qt analogs at the Q level, right? Qt level.
Yeah.
And U, the number of U, so let's say you have U1 and U2, it corresponds to the character variety of genus G being equal to 2.
Mm-hmm.
The issue here is, in this case, it works well because this product is kind of balanced in the sense you have this product over this product over this product, but when you add an extra U2, it becomes unbalanced. So, for instance, all of the enumerative tools that I used for all types, but let's say in this case, you have that kind of hidden behind the fact that this product is kind of balanced. You have something and you divide by it. So in order to extend those notions and to have a U1 and U2,
Yes.
it's an open problem, it's a conjecture, and it's not, it has not been done yet, even at the Q level.
Okay, because my motivation would be, you said that if the Z was H before, or the Z square was H square, then the cancellation appears and you just have T-core partitions left in one case, yeah?
Yeah.
But if you have a Q and a T, then you might be able to have to separate the H square in two different factors, let's say, and you could cancel one with one variable and another one with a second variable, something like that.
Yeah,
so that's
actually
not completely symmetric. Yeah. So also the H, maybe you don't. Yeah. Yeah. So somehow maybe the H square in the denominator, maybe that can also be split into different factors.
Yeah.
Or is that not possible?
So my approach to it, basically, if you think of it as a filtration,
yeah,
on this, if you add a U1 and you want to use a polynomiality argument, which you can use in the case of U1 and U2 at the Q level,
yeah,
basically the natural filtration that's going to appear is some specific calculus and computation on T1 and T2 for partition. Let's say you take U being Q to the power of T1 and U2 being Q to the power of T2. So and that's an interesting lead that I was considering at some point, but I got taken away by some other things. But yeah, I tried to reformulate this U2 and U1 product as some kind of symmetric by just multiplying and dividing. But I was not able to actually quite really symmetrize it.
Okay, I see. Well, anyway, you had similar thoughts, so you already tried in that direction.
Yeah,
So,
but
yeah.
yeah, maybe I took it in the wrong way. I mean, if you have any idea, I'd be more than happy to discuss it and hear about it. I mean, I'd be really glad, to be honest. I mean, to me, if I want to use the enumerative results that I showed you for type A, I first need to symmetrize this product in some sort. So this is like my main concern if I want to get a U1 and a U2. And at this level, it's even worse in the sense that this is a QT polynomial. So the polynomiality argument that I'm using for all of the formulas, actually it fails.
Okay, yeah. Okay, well, thank you. Yeah.
Okay, thank you. Any other comments or questions? So if not, can you please unmute and thank the speaker?